All right, looks like we are live. It's kind of like really we are kind of staring at those lights and looking for the green signal to get started. Anyways, good afternoon, everybody. Hope you're having a great time at Build. My name is Gaurav Seth. I work as a lead program manager on the Chakra JavaScript engine. The Chakra JavaScript engine powers two key things on the Windows platform. First, it powers all the Windows Store applications written using HTML, JavaScript, and CSS. And second is that it powers Internet Explorer starting Internet Explorer 9, kind of obvious. I've been on the engine for a long time. I've been working on it since its inception, so I've kind of worked on all the areas. If you have questions, I'll be very happy to answer those. Meet me after the session. I'll be at the Visual Studio booth all day tomorrow morning. Come see me. I'd love to talk to all of you about anything to do with JavaScript. One of the very interesting things in my role at this point, which is like extremely, extremely interesting and extremely challenging at the same time, is when it comes to performance, my job is to make sure that the Chakra JavaScript engine is second to none in the market. That makes me write a lot of JavaScript code, analyze a lot of JavaScript code, trying to keep finding patterns as to how to make the code run faster, how to make our engine run faster. Now, let me ask you guys a quick question. How many of you have actually written JavaScript code here? Great. And how many of you have actually been trying to improve the raw throughput of your JavaScript code? Great. So, I kind of feel that I'm completely connected to you. I totally know what you do because to keep my job, I do what you guys do. I keep writing JavaScript code. I keep analyzing JavaScript code. Where is the time getting spent, man? Give me my time back. For the rest of you, who've not written JavaScript code, the thing that I want to talk about today is how do you really improve the raw performance of your JavaScript code? I have a pretty packed agenda. I'll show you tons and tons of code snippets. We'll have a demo. We'll do some demo editing. We'll see how the app is performing. For some of you, even though I'll tell you that, don't go to the nits of the code, I know you guys would say hey, can you give me the code? Can you show me the code? So I'll give you the, code samples, the raw JavaScript code that you can play along with or download and play later. And by the end, my agenda is that all of you go back with 5 principles that you should always remember in terms of working on JavaScript. 5 principles to improve the raw JavaScript performance of your code. Now, performance is very, very diverse. I could come from different perspectives. I could write books and books on it. There's one perspective I'm going to come from because I work on the Chakra engine is help you understand what modern JavaScript engines like Chakra do with your code, and so that you can write better code which performs much better. Now, even though I'm coming from the perspective of Chakra, the thing that I would say is these 5 principles are in general applicable to all the modern engines and the modern browsers are there. So it'll work on Chrome, it'll work on Firefox and all. Next, let me introduce you to the demo that I'm going to be using in this session today, High5 Yeah. Let me actually... So High5 Yeah is a single-player casual game that we kind of created. And what it does is, let's go take a look. It's a fun game. I have a matrix. It has a bunch of players. All the players are object with properties like north, south, east, west, and they're kind of having their hands 90 degrees. I touch a particular pair, and they start rotating. When they rotate, they touch the player adjacent, or they touch a neighbor's hand, they give a high five. The aim of this game is touch a player which can generate the maximum number of high fives. So you'll see that there is a score that I'm keeping in terms of the highest number of high fives that I can create. Now, one of the things that as I was developing this game was I added this cool slider to see the size and see how the difficulty level of the game improves as I reduce the players, go up, go low. And one of the other things I did was okay, I've made it really dense. Wow, this makes the game actually go pretty easy. But now, given that I was talking on performance, what I did was I also ended up creating a benchmark mode in this game. And what this benchmark mode really does is that I start with the known state of the board. I start from a known point so that I can measure the time it is taking to do all these rotations. So let me go click this, and you'll kind of figure out. So now that I'm playing in a benchmark mode, it is an array of 26 elements, and they're all rotating again and again, and you'll see that it goes till a point and then repeats. So the array resets, and the benchmark continues. Now, that's the game. Fun, cool, like it? Great. Now, so I just mentioned that the nits are not in the code, but I know some of you would want to get the raw JavaScript code. So the raw JavaScript code for, that is powering this application, the entire logic, is at that, mini URL. You can go download it. It is aka.ms/fastjs. Now, one thing, when you download it, it might take anywhere between 10 to 60 seconds, depending upon the browser that you're using, because it is kind of executing that game 100 times over to calculate a score and calculate a timing. The first thing is, like, when you're looking at JavaScript, try to extract JavaScript, get rid of all the DOM pieces, and kind of measure that performance. So go grab that now or later. That's fine. And let's now look at like what this game is composed of. This game had a matrix of players. Each player was an object with 4 properties, as I mentioned: north, south, east, west, kind of pointing where it's where the object is pointing. It had an on-touch event handler wherein I was doing the arithmetic about, hey, okay, start from this point, go here, go there, and that's how you do it. And then it's the animation loop, wherein what the game does is, for a given player, you generate the list of all the neighbors to rotate. Then you rotate the player, and then you keep doing this till all the players in your neighbors list get rotated, and there are no more moves to happen. So in terms of what's happening in the game, or what are the pieces of the game, there is arrays, there are objects and object properties, there are numbers, there is an animation loop where you really need to be perf critical, and overall the goal is that we should stay lean in terms of memory allocation. So these are the 5 areas that I will be covering in a while, but things that are really important from the perspective of improving the raw JavaScript performance. Now, one of the first things when I wrote the benchmark that I noticed was, like, the game actually was not having a great throughput. Like, when I wrote the benchmark, I started running it. What I noticed was that the throughput was not really coming out to be around 60 frames per second. Why does it matter? Like, 60 frames per second is typically what a human eye sees, right? And what happens if your game is not performing at that level is that the user experience has a glitch. For very visually appealing apps, it's like, yeah, there is some jarry experience. There are some glitches when you're loading web pages. There will be, it's not coming up properly. So there are glitches to user experiences, which we all want to avoid. Now, what kind of creates, or what are the key components of these, that impact the visual throughput of an app? There are 2 key things. First is the different subsystems of the web browser stack. For IE, we kind of divide the different subsystems right from networking to the layout and rendering piece. There are 11 different subsystems in IE that we kind of classify. And the second thing is the code that we write, because it's the code that we write which drives all these components and make them do work. And what really matters is that the web stack is inherently single-threaded in nature. Like, the engines, the browsers, they kind of keep doing multiple-threaded things, but inherently in terms of code execution, it is single-threaded. And what really matters is that you really have to paint onto the screen within 16 milliseconds to get a 60 frames per second rate, right? And it's our code that is driving this. So if we drive the code in a very different way, or write the code in a very different way, we might miss a beat, or we might not be able to paint in 16 milliseconds. And that means that your user's experience will have glitches. So that is the whole purpose of this talk. So I'll be talking about how we can make sure that we are able to achieve this kind of responsiveness from a raw JavaScript perspective. Now, getting back to the app, right? The first thing that I started doing was, let's investigate. Let's look at some power tools and see, like, hey, how do I really get to the guts of what is happening in this code? The first best practice that I would say is always start with a good profiler. Now, there are a couple of profilers that I show on the screen. On the left is the awesome new F12 UI responsiveness tool. Like, how many of you have actually seen this tool already or have heard about it? So Jonathan Carter is going to be going pretty deep into this particular tool tomorrow morning. I would definitely recommend this, going and attending that talk. But this is like one of the new tools that we are shipping with the i11 F12 developer tools. It kind of gives you a, good construction of like where is time being spent, what is the frequency per second of your app, and what subsystems are taking what amount of time when you profile your app. The one on the right is Windows Performance Analysis Toolkit, ships free as part of the Windows SDK. You can download it and use it to profile any application that is executing on the Windows platform, including web pages, including IE, including the Chakra engine, including the other browsers. So very, very handy tools. I would definitely recommend going and looking at it. So now when I started looking at the perf profile of my application, there are certain things that I saw on these profiles. Now the profilers, let's take a minute to see what they actually measure. What they measure is that on the y-axis they measured the percentage CPU utilization by your app. On the x-axis is the time that your app is running, and then they kind of break it out into the different subsystems that I talked about, in different colors. Now I'll be focusing on two subsystems. The one in purple, which is the JavaScript code that we write, and the one in blue, which is, it could be shown as Chakra, or different tools show different things. So some might call it GC, some might call it, etc. Now the key thing to remember is JavaScript is extremely flexible, right? We all know about it, and I've been talking a lot because the thing was I want to get through this section very quickly and get to the principles. The thing is, you can write two extremely different pieces of code which produce the same functional result, and your code can actually make the JavaScript engines do a lot more work. So, let's stay focused on these two things, and let's continue. Now, the first thing that I noticed when I actually profiled my app was there was a lot of garbage collection happening, and that is seen here. When there's a lot of collection happening, the question is of course there is a lot of garbage collection happening. Do I expect it? No. But what's wrong is that probably there is a lot of allocation also happening in my app, be it explicit, be it implicit. I don't know what's going wrong. So with that starts my first principle. Now this is from where the real stuff starts, right? Always make sure that in terms of the memory allocation of your apps, you stay lean. Now let's get back to the app that I just showed you and figure out where the time was being spent. So let's go to the code. And I'm going to start with one of the very obvious things, right? Is the code size okay? Can you guys see it at the back? Or do you guys want me to make it a little bigger? Okay. Is it good now? Cool. So what is happening is let's see in terms of explicit allocations that are happening in the app. Of course, am I creating objects? So I start with searching for new, where all am I creating new in my. So this is the beginning of my app. I kind of create a matrix. There are some temporary arrays that I'm creating. It's fine. Let's keep going. There are two kinds of players that I create on my app. There are two different sets. If you notice, there was one in blue. There was one in yellow. So we call them their name is Jody and Mia. Good to get introduced to them. Then in terms of initializing, I was kind of filling up my array board initially in terms of a two-dimensional array. So this is the call which I was making, wherein what I'm doing is, this is the benchmark code wherein I start with a known state. So I'm just filling up the array with the known set of players and the known orientation. This one is when I'm outside of my benchmark mode, I kind of start creating an object pool. I start with my game from an object pool, because one of the key things in terms of object allocations that you should try to remember is always try and use object pools. They're much better in terms of trying to keep your memory constrained and not create a lot of allocations, and try to work with the object pools that you end up creating. Now it's the same thing, I'm still creating those objects. Now in terms of the rotate function, right, that I talked about, what is happening is you start with an object, you have to rotate it initially, and then as you touch all of the neighbors, every object has to be rotated. In this function, what I was doing is that I check in this line of code that if a player was pointing northeast, what needs to happen is I now need to make it point east and south, right? It's a 90-degree rotation clockwise. And so I create that. I was using a temporary buffer, as you can see, this temp matrix, and I was kind of pushing into it okay, I really need this player to actually move to east-south direction. And if I go to the next function that gets called was the committing of that rotation, wherein I actually go and update my board. Now, what was happening in this piece of code is like, if you will look at it, now, if I said that the player had to be moved north and east, I kind of checked, what was the player's current orientation, where is it going to go, and if it was going to go northeast, I create two new objects, either like not two new objects, either Jody or Mia based on what direction they're going to go. So I was, instead of using my object pool, I started creating a lot more objects, right? Because every time that I was doing a rotation, I did not update the properties of my object, but I actually created a new object saying that, hey, you're actually creating a new object with the right set of directions. Now, the way I will fix it, is that I'm going to change these methods to I'm going to go save it, and let's go to the definition of these methods. Now, I just changed them to rotate fast and commit fast. Of course, that does not mean anything until I show you the code. So now what is happening was like I changed both my rotation function as well as my commit functions to do one thing, that instead of pushing the the new direction, what I'm saying is like I need to work on the given object pool. So what you do is for a given player at X and Y location, now you say that the north property becomes 0 and the south property becomes 1, if the player was at northeast direction initially. So you're making a 60-degree clockwise move, but you're not going to be creating more objects. You're just going to be working on the same objects. And in terms of commit fast, that's right here. In terms of the committing of the rotation, instead of creating new players, all I started doing is like, okay, start using the same object pool and then kind of keep working on it. So this, let's just make sure that the app is running. Yeah. So, one of the things you'll notice is that in terms of my frames per second, I'm not yet up there because there are probably other issues, but there are other things happening in the app. In terms of the raw JavaScript code that I actually shared, and in terms of the perf profiles that I took after I made this change, let's see what happens. On the top is the GC profiles that I took with this app. Now my total allocations or the total collections actually reduced by 1/3, and the raw throughput of my JavaScript application actually improved by over 3 times. That's a great thing. Like we don't typically imagine that allocations would be so expensive, etc. But they are quite expensive because allocations kind of cause GC, and GCs are in general bad. Now, in terms of garbage collection, it's kind of hard to conceptualize. I could spend an hour on garbage collections itself, but let's try to take a view of what happens in garbage collectors in JavaScript engines. Now, let's imagine that we have 4 set of pages kind of separated into 2 pools. There is a memory, there is a small object pool on the left, and there is a large objects pool on the right. That's what garbage collectors typically maintain. That's the heap memory that we call it. You have your program that is running. Now, in terms of mark and sweep collectors, it's typically the 2 phases that happen, but let's just break them down into 4 phases. In the first phase, what happens? Your program was running, the garbage collector gets initialized. At that point, it pauses your program. Your program stops running. Now, the thing to note is there are certain blocks that I kind of indicated in black. The GC at this point in time does not know that this is garbage. This is just like I'm telling you that this is going to be garbage and this is going to be collected in the next phase. In the initialized phase, one of the other things that garbage collectors do is they kind of go scan the stack, figure out what thing is where and what are the kind of dependencies. In the next phase, which is the most important phase, is the mark phase. In this phase, the garbage collectors actually start going through all the objects in your garbage collector, figuring out their dependency change, what objects are actually garbage, what objects are actually still being used, and they kind of mark them that, okay, these objects are actually garbage and they can be collected. In the sweep phase, the garbage collector actually goes and cleans up all of that memory and say, okay, all of these objects can be deleted. And finally, they kind of zero out those pages, and if needed, they kind of return some of those pages to the operating system so that we're kind of staying lean in terms of using memory, etc. And then your program starts executing. So there's a lot that happens, and there is a pause in between. Like your program was paused for all this while a garbage collector was working. Now, what triggers garbage collection, right? That was a flow, like you got paused, but what triggers garbage collection? Every call to new that you make, or any implicit memory allocation, reserves memory in the GC. Like in terms of reserving memory, what it means is that it'll go to the memory pool and say, give me some memory. Now, all these allocations are cheap till the pools have memory. As soon as the pool gets full, engines are forced to do a collection, right? Collection create pauses, and pauses could be milliseconds long. They could actually be more than 16 milliseconds long if you're not writing your code appropriately, and there's a lot of collection that is happening. So it could cause glitches for your end user experience. So the key thing is be very careful of the object allocation patterns in your apps, because every allocation is actually in a way getting you closer to a GC pause, right? Now, I just told you, like, okay, we need to be aware of the patterns, etc. But there are things that we also do from the JavaScript engine's perspective in Chakra. One of the things we do to make sure that these pauses are really reduced is that we have a concurrent architecture for our garbage collector, wherein we do a lot of those phases. Like if you look at it, I've kind of split it out. Those 4 phases are now split out into 7 or 8 phases. Some of them happening on the main foreground thread, and some of them actually happening in the background thread. What this kind of an architecture enables in Chakra is that it helps you achieve smaller pauses. Like your apps would actually pause for very little time in terms of UI responsiveness. That's very good. The other key advantage of using a background thread for GC is that we can actually collect a lot of heuristics about what was when was the last collection that happened, how much memory was collected in that, how successful was that allocation, etc., to be able to say that we can now actually go and do partial and time-constrained collections. We call this quasi-generational GC. And that's the technique that we use in Chakra to make sure that whatever code you're using or whatever programs you're running do not create a lot of pauses even when the garbage collection is happening. Just in terms of my app, one of the things that we've actually added in Chakra in I11 are a lot of enhancements in terms of moving stuff down more from the foreground thread to the background thread. In terms of my app, actually more than 60% of the time that was being spent in the foreground thread now happens in the background thread. So your apps automatically become more responsive. Like they're doing a lot less work on the foreground thread when collections are happening. And this kind of brings me to the best practices that you should always keep in mind when you're thinking about collections. I know this is like collections is one of that very, very deep subjects. We can spend a couple of hours just talking about garbage collectors. But the key things are never try to create objects if they are not needed. Like be aware of it. Second, try to use object pool, especially when you're creating all these new rich apps. You're trying to create a lot of games. You're trying to create a lot of objects. Try to use object pools when possible. And third is be aware of the allocation patterns of your app. Now, a couple of quick things or quick patterns that I often end up seeing in terms of what people end up doing and what is causing garbage collection. People typically end up putting a lot of closures to event handlers. Like you need to delete them. That memory will keep hanging in the garbage collector till you actually go clean them. We keep inserting DOM trees, DOM subtrees dynamically into the code. All of them are actually creating a lot of allocations to happen in the engine. And the third thing is be aware of the implicit allocations done in the engine. The engine also does a lot of work. It creates a lot of types. So be aware of all the implicit allocations in the engine. Any questions till this point? Go for it.
Is the object pool a language feature, or is that just talking generally about object pool?
Just talking generally, it's like, I was kind of giving you a visual of, how GCs manage the memory. So, you could have different object. No, so in terms of the object pools that I showed, it's not a feature of the GC, but it's in general a good idea for all of us to go actually create an object pool to work with instead of creating more and more objects on the fly and then kind of let the GC do the work.
So is it better to create and remove properties from an object that exists?
Yes.
Than to create a new object?
Yes, yes. Now, the last thing or the last statement that I talked about or said in my last slide was be aware of the implicit allocations that the engines do. And this is a great segue into my next slide, or the next principle, which is always use fast objects and do fast manipulations on your objects. Now, unlike static languages and dynamic languages like Chakra, the internal representation of objects is created at the runtime. That means when your code is executed. And this is because JavaScript engines do not really know the shape of your object till you actually start executing them. So given that it happens at runtime, let's take a piece of code and see how it happens. When I execute the first line of this code, when I say var p1 gets executed in the engine, we start with the base type. It is just a null object. Every object starts with this kind of a type. When the line executes p1.north equals 1, we kind of evolve that type into another type and add north and 1 in the first property at this slot index, I'm adding this property. When I add south, again it evolves. Three key things to remember. These types that are being created are like native structs. They're like vtables. Very fast in terms of, okay, I know this property ID and the slot index, the engine and the compiler can actually go and work on it very quickly. Now, so that's the first thing. The second thing, these types evolve over a period of time. Now, if I was to create another object foo, which had the same properties north and south, the engines would actually go and use the same type that was created. So the type evolution would not happen, right? Because it's already evolved, I'm already using it. And that is the third key thing, that in terms of the implicit allocations, I just showed you an example of one object, two properties. But think if you're creating multiple thousands of objects, each with a different shape, what is going to happen? There's just one caveat to always remember. The objects, if you change the shape of the object and kind of reverse the ordering of the properties or mix up the ordering of the properties, engines would do more evolution and they would end up creating more types. Now, in this case, in the second example, what I ended up doing was instead of having north and south, I added south and north, which means the engine had to do more implicit allocations, kind of derive a new type. And the key thing is these two types do not match. So this leads to type mismatches for the JavaScript compilers. And that is really bad because the JavaScript compilers try to make assumptions based on the type information of the objects. So the key is always try to keep the shape of your objects the same in terms of how you're adding properties, how you're creating those objects, and kind of use the same set of types again and again. Now, there are two key examples that I wanted to go through in terms of what are the common mistakes that I see in this area. The first one in terms of type mismatch happens when you start adding properties conditionally in your object constructors. In this case, the code on the left, based upon the direction in which I wanted to point, I start adding properties. And by the end, what you will see is when I kind of instantiate P1 and P2, their types are not going to be the same. So the takeaway, add all the properties, use special values to say whether they are available or they are not available. The second key mistake that happens here is don't try to avoid defaulting properties on the prototypes of your object constructors. Engines do not go all the way up to the prototypes of the object constructor to figure out types. That is expensive. So try to, again, add all of them to your object constructor itself rather than kind of creating it on the prototype. In this case, what you will notice is in the code on the left, I had, I have a player constructor, but I kind of create those properties on the prototype of that object. And then when I, add N and north and south properties to P1 and P2, at that point, P1, P2, P3, everything has a different prototype or a different type for, that is used inside the engine. So again, add all of them in the object constructor. Now, world would have been really ideal from a performance perspective, from a JavaScript engine's perspective, if everything that was ever created was always a fast type. But there are specific cases in which we kind of end up creating slower property bags. And when I say slower property bags, think of them as just key value pairs. They're like just hash tables, much slower lookup. Everything goes into a bag and just sits there. Now, in this particular code snippet, if the player object was a slower property bag, and I add north and south properties, it'll create a new slower property bag. Let's call it P1 for now. And if I have exact same piece of code creating another object of the same type in the same property ordering, it'll end up creating another property bag, and those two property bags do not match. That is the big difference between slower property bags and the fast types. They do not match. Even every object, if you have the same shape, everything, it does not matter. Now, three key things that, or three typical cases that I'll call out wherein the engines do end up creating slower property bags. The first one is you start with a fast property, fast internal type, start deleting properties on it. Engines would de-optimize that. Like they will say, we don't really know, what the goal of the code is. Probably there are a lot of deletions that are happening. So avoid deleting properties on your fast types that you create. Instead of deleting those properties or elements, try to assign or have specific values that you could use to kind of say that, okay, this is not usable, this is usable, this was deleted, this was not deleted. The next thing is, in terms of when you're adding more and more properties to your objects, what tends to happen is like every engine has kind of a threshold at which point they say that I'm going to stop evolving the types, because in terms of type evolution, there are a lot of types that get created in between. And all those are implicit allocations that are happening as your code is running. The key tip here is, as long as you are in the tens of properties, so I'm talking about units, like as long as you are in tens, it's okay. But typically don't try to go into hundreds of properties. And you might say, like, I never end up adding, like, who will add 100 properties? Like the example you have up there, you're adding 256 properties. Guy, you're crazy. But that's not the case. When we try to kind of achieve the prototype-based inheritance, we actually get a lot of code that is not written by us, and we start deriving from it, and we kind of start creating objects. So the key thing to remember is when you do such things, see what is the, how many properties, etc., are being created in your base objects that you're deriving from, because those could lead to slower property bags that you're not even aware of. And sorry, so this was, I didn't move the slide. This is actually the sample that I was talking about all this while, wherein I have 256 properties that were getting created in my constructor. And on the other side, it's like restrict those properties, figure out whether you are, whether you really need to use an array or, what is the thing. The third case in which the engines do end up creating slower property bags, and this is an interesting one, is getters and setters. Like when you start creating objects with getters, setters, and property descriptors, all of these are like new JavaScript features that were introduced in ECMAScript 5. And they have been supported in all, I think, major browsers and engines in the last couple of years. I think we've been supporting them since IE9. We do end up creating slower property bags. Like if I was at this conference last year, I would have said, like, do not use these at all. But the thing is, in terms of the adoption that is happening, engines have started optimizing these cases a little bit. For example, in Chakra in I11, we do now create inline functions for these getter calls. So the getter calls are getting faster and faster. But the key thing is, like, they have a great capability set that they provide, but differentiate and do not use this in your code path, which is really perf critical. So think about it like, do you want to have perf, or do you want to have these capabilities that you want to try and use? Now, all that said about the objects and the shape of properties and internal types, let's go back to the demo and try to see if I can go and fix the demo and kind of make it go more fast. So in terms of what I was doing in my demo, as I said, there are two players, Jody and Mia, and I'm actually just deriving them from my player type, right? So there is Jody. I just say that, okay, you create Jody, have its name, and it derives from a player type. Now, what is a player type? In terms of a player type, I actually, given that there were some optimizations that were happening, I actually wanted to kind of measure the performance of inlining and like how it is performing, etc. But I ended up creating my player objects with getters and setters, with having like enumerable as true, configurable as true, just kind of playing along with it. But that kind of really hit my performance. Now, the thing that I will be doing is, like, given that it's like really perf critical, I will just be moving to vanilla properties for now, which is like my fast player object. So I'm just going to go back. go back to my app and kind of start executing that app. So there's still more work to be done, but in terms of the performance, let's look at the raw throughput that you might see from the JavaScript code that I kind of shared out. What was actually happening in the app, and let's figure out where we are in terms of the performance of the app. Now, what I noticed with this is that on the top, like the pieces in purple are the script execution time, and I'm not sure if you could read the x-axis, so that's why I've kind of written up the timings that I see in the profilers. But the amount of time that I was spending in script has actually gone down from 3.8 seconds to 2.2 seconds, or that's like a 30% gains. And in terms of the raw throughput, like if you're kind of using the JavaScript code that I shared with you, when you start creating fast objects, you're actually now at 5x of your original cost, like just these two tweaks, and you're 5x from where you started. And just in terms of numbers, that particular JavaScript code is doing around 11,000 rotations, 100 times over, and now it's happening in around 2,000 milliseconds. So that means like my throughput is like in every millisecond, I can actually do 5,500 rotations, which is like fairly good, right? Would you guys agree? Okay, so there's probably something else that's going on. And now I'll stop for a minute in terms of updating the demo, but kind of walk you through the remaining couple of principles and kind of close down on the object stuff. Now, one thing that I said earlier was like you should try and avoid type mismatches, but why should you do that? In terms of type mismatches, there's a very important concept called inline caches. So all JavaScript compilers actually create inline caches for property accesses at a given call site. A lot of jargon. I don't know whether you guys got it or not. Let's talk about it from a JavaScript perspective and kind of run through this code. I'm creating my player objects. All of them are type 1, right? I have a rotation function to rotate my players. Let's keep going on. Then in my for loop, what I'm doing is I'm trying to initialize all my players, right? So I create all my players. All of them get created as type 1. Now, in the line in blue, I actually take the last player and add an extra property on that player saying that, hey, this is my last player, so let's have a last property and say that is true. Now, the type of that object actually changes. It is no longer type 1, but it is type 2. And then I start calling rotate in a for loop for all the objects. Now, the line in green, when I start calling the rotation, what is happening is, in terms of what's happening in the code, is you're accessing the nth property or the north property on the player object, right? The first time the engines go through this, they figure out that your player that you're sending at this particular call site. So this is what we call a call site, wherein you're accessing the nth property of a particular object. The first time the engine sees, you're sending type 1. So let me actually create an inline cache in terms of the native code that I'm going to be generating or the compiled code that I'm going to be generating. So they kind of insert a cache for it inline so that further lookups are very, very quick. Now, as we keep going through these objects, like everything will hit the inline cache, but for the last object. And when the last object comes, which is not of the same type, the engine would kind of not really de-optimize, but go the slow route, and it'll miss caches, and the lookups will be slow, and your code would run slow. It would not only happen for the last case, but also happen for the first case if you were going to do this recursively, right? And in terms of numbers, if the board size was 16, you miss it for the last one and the first one. That's like 2 out of 16, 12.5% of the times you're going to be missing the inline caches. Now, starting I11, one of the things that we are supporting in Chakra is that we are also supporting polymorphic inline caches. What it really means is that we can create caches for multiple types at a given call site. Now, in this particular piece of code, I create a player of type Jody, say type 1. I create a player of type Mia, say type 2. And then when I go through this, I'm kind of distributing them almost evenly, and then I'm calling the rotate function. At this point at p.n, once both type 1 and type 2 come there, I would create an inline cache at that given point. Now, this is a bit confusing. Like in all of my slides, I've typically had the slow pieces on the left and the fast pieces on the right. Like, what is the key takeaway from this slide? Two things. Polymorphic inline caches are very helpful in the cases where you really cannot create objects of one given type. Like, there are cases we just cannot work with objects of one type. Like, they're really fast, they're really helpful in improving the speed and performance of your applications. But in general, if possible, always try to use monomorphic caches, which is like caches of single type, which is like the left side example, because they're much faster. In terms of the polymorphic caches, what happens is, think of it that engine would have something like a switch statement in between, right? So if you're doing it in your, in a loop and it is really perf intensive, there is more work that the engine does. So try to use monomorphic caches or caches of single type most of the times. If not possible, try to use polymorphic caching and try to distribute your objects kind of evenly so that, it's not like the last object that comes is of a different type wherein cache misses happen. Now, in terms of the pure impact of these inline caches, if you go back to the JavaScript code that I've shared and kind of use one object as a fast player type and one object as a player type. So one is a fast object, the other one is a slower property bag. The impact of performance, like in terms of from where we came from the original code, I would have regressed 2x. That's a lot of performance. And the thing to note here is in terms of the slower property bags, the engine always miss inline caches because they don't cache anything from the slower property bags. So there is a lot of performance boost that comes just because of these kind of inline caches that are created by the engine. So key takeaways, always create and use fast types. Keep shapes of your objects consistent, which is basically the property ordering. Always try to avoid mismatches for fast types and avoid inline cache misses for the code that you are creating. Now let's talk a little bit about numbers and see what are the allocation patterns and what happens in terms of numbers in JavaScript. So JavaScript has only one numbering system. Everything is IEEE 64-bit floating points. Great for flexibility, but it's a big performance and optimization challenge, both in terms of the execution time and the space allocation that happens in the engine. So there are two key concepts that you need to remember. So engines typically have, so how many of you know about stacks and heap? I hope most of you. Stacks pretty fast, kind of fixed sizes. Heap is what we get from the GC, kind of slow to access. You kind of getting into that garbage collection mode, etc. Two key things. Engines typically try to use the stack to put 31-bit integer values onto the stack always. And the way they do it is they use the least significant bit on the stack to kind of say whether a value is an object pointer or a value is a 31-bit integer. We call this process tagging, so we call them like tagged integers. So 31-bit integers, like as long as you're doing 31-bit math, always stays on the stack. Now if you start using 32-bit integers or you start using floats, they actually have to be created in the heap. So everything that comes from the memory pools that I showed you, it is slower both in terms of the allocation that is making, plus the operation that we call boxing, that actually we have to go fetch that memory, create that memory. So always try to use 31-bit integers for math. JavaScript is extremely flexible, but be aware in terms of when you're writing objects, like do you really want to add integer, 31-bit integer versus you want to have some text there in terms of representing your properties and directions. You want to have some float values, etc. All of the other ones are slow. Of course, the 31-bit arithmetic is faster. To avoid creating floats, a lot of times what we see in code is like people use floats but then kind of throw away everything that they had created by kind of rounding it off at the end. After your code is out of the perf critical path, avoid doing that. Now, one of the tips that, one of the questions that always keeps coming up is how do I tell the engine to, always try to optimize for integer math? One of the best trick is use OR 0. Internally, the compiler makes a lot of assumptions in terms of generating code, and this is one of the assumptions that typically all compilers look at, to assume that if you're writing this pattern, you're probably going to be working with integers, so all the code that it generates is going to be type specialized for integer math. And given that I talk about type specialization, let's try to understand what it is. In general, when the compilers create the native code, there is some amount of generic machine code based on a lot of assumptions that you create. Now, when we work with arithmetic, one of the things that happens is engines try to make very, very strong assumptions about, are you going to use integer stuff, are you going to use floating point, and they create very small size, super optimized code, but which would work only for a given numeric type, like be it integers, be it floats. Now, in this particular sample, what I'm doing is I'm creating a distance method to calculate the distance between 2 points, and then I start calling it with point 1, point 2. what is happening here is I'm actually the argument types are not consistent. So I'm kind of passing both integers and floats. And what happens in such cases when the engine had kind of made some assumptions, kind of created either this kind of a function type specialized for integers, was that it'll say that, okay, I'm going to bail out because I'm getting different values, so I cannot really have this super optimal code. So it'll go to an unoptimized version, again try to make assumptions, again try to optimize this. So the right way when you have both integers and floats is to write a distance method that takes integers only and does only integer math, and one which does only float math. Like both of them could be type specialized, both of them could run super, super fast. Now, so in terms of like summarizing it, always try to use 31 integer math when possible, avoid floats when possible, and allow engines to do type specialization. Now let's talk about arrays a little bit, because that's my fourth principle, that you should always use fast arrays. Now, just like objects, and their internal representation, the internal representation of arrays also evolves over a period of time as you start executing your code. Now, let's see how the engines manage the different array types. Now, when I execute the first line of code, notice that I've not given it any size. Engines typically assume that you're going to probably be creating an integer array. They reserve a block of, say, n size. It's typically less than 10. For Chakra, it's around, I think, 4 or 6. That we allocate in the heap. Now, in terms of the next line, when I go and add the first element, it knows that, okay, it was an integer value, so let me use this particular array type and add the value 1 in slot 1. Now, next what happens is it sees, like when I am adding a float value to that array, it says like, okay, my assumption has actually gone wrong. What it does, it ends up creating another new array, which is of float type. It ends up copying the value 1 from the previous array to the new array, and then actually goes and adds that float value. Next, when I execute the last line, it's like, okay, I made an assumption, it again went wrong. Now it's actually a var array. Think of a var array as a generic object array that you could work with. Now again, both the things happen. You added up doing another implicit allocation. So we have to do, the engine creates another float array or a var array, or creates a var array or a generic object array, copies all the values, and then goes and stores strings. So if you were going to use var arrays, notice that there were a bunch of implicit allocations that the engine ended up doing. Think just to be aware of. Now, in terms of best practices, I think 4 or 5 points here. First, always try to pre-allocate your arrays. The engines start with, like, if you don't do that and start adding properties in the end, engines would start with some small size that they kind of allocate initially, but then kind of start adding properties. So it'll be a fragmented segments maintained in a linked list, and your accesses will be slow. If possible, always try to create arrays with, give them a length initially itself. But one thing to remember is, like, if you're going to create an array of 64,000 elements and you're really going to let it be sparse, don't end up creating that big an array, because try to optimize and balance, like whether you want to go for memory or whether you're going to go for speed. Now, the next thing is in terms of the implicit conversions that I talked about, right? Like we were converting from a int array to a float array to a var array. If you're going to do this in your code, there are cases like, first, try and avoid it. If you have to do it, make sure you're not doing it in the perf critical path. And one of the ways you can do it is like provide a hint early to the compiler. So if you look at the code on the right, the second line in green is like provide a hint early to the compiler so that we initially only start a var array and kind of can work with it. But the key thing is still try to avoid using these, and let's talk about it why. Now, a key concept that got added and is supported by all the JavaScript engines now is like this technique called typed arrays, right? So you can go create typed arrays. What are typed arrays? It's an explicit relationship or explicit typing that the code you're writing is telling the JavaScript compiler. So you can go create a float64 array or an int32 array. So you're explicitly telling the compiler that, okay, all of my values are going to be integers or all of my values are going to be floats. And the engine knows, okay, I need to optimize, I know how to optimize these values. So the thing that the compiler does for typed arrays is it just creates a binary blob instead of doing all those, type transitions, etc., and start working on it, which is much, much faster. So if possible, always try to use typed arrays. Now, when we added this feature in IE10, one of the questions we went back and asked was like, hey, we have this awesome new cool feature about typed arrays. They're so much faster than the numeric arrays that are generally available in terms of this type transition. Won't it be so cool if like we made all numeric arrays behave like typed arrays internally? And yes, starting IE11, Chakra treats all your numeric arrays as typed arrays internally. But one of the key things here that you really need to note about is try to make sure that you keep the types or the values of your array of a consistent type. Like don't mix strings and floats and integers, and even don't mix ints and floats, because the key thing is that in terms of flexibility, it's just some sugar that we have added, but we really need to respect the flexibility that the language provides. And unlike typed arrays, what happens in this case is like if I created a float array, I was working with the float array, you add a string, I would actually have to de-optimize all of this stuff. Now, kind of give you a var array to work with. And so there's a lot of work that happens within. So key things, create and use numeric arrays. Make sure you're not mixing the different types, even like ints and floats. Keep them separate. Next, make sure you don't start deleting elements from your array. Again, goes back to the same point. Like if you're using a numeric array, the key thing would be that deleting a property, it'll become like undefined. Undefined is a 64-point special value that the engine looks. There would be a lot of de-optimizations that are happening. Again, try to use and give a specific value instead of using, kind of deleting the value. So keep your arrays dense, keep working on them, use specific values. Now, the last thing about arrays that I wanted to talk about, this is a very common pattern, a very common question. Like, how do you actually enumerate on your arrays? Like, there are multiple things. On the left-hand side, you will see there is, foreign. You could use for each, and then you can enumerate using the length property, right? Now, always try to cache that property instead of using it in your foreign, in terms of your for loops, because when you cache those properties ahead of time, it almost becomes like a constant to the engine. So there is not even a lookup. Like in terms of a lookup, yes, there would be an inline cache that would get created. But if you kind of cache it outside, it will be like a constant for the engine that is happening at that point. So always try to use it, one of the most common things that I see. Now, kind of summarizing it, always try to pre-allocate your arrays. Keep their type consistent. You use typed arrays whenever possible. Keep your arrays dense and enumerate them efficiently. Now, this is the last principle that I'm going to be talking about, which is always try to optimize your code and algorithm to do less work in general, and specifically less cross-subsystem work. Like even though JavaScript engines have really become fast, they kind of like with JIT compilers, now we are running super quick. People say like, okay, in terms of native and JavaScript, the difference is around like 2x, 3x, 1.5x, 1x. They're getting closer. They're going to get there. Maybe a couple of years, yes. But the key thing is whenever cross-subsystem calls happen, it is very, very slow. It's really slow. Avoid chattiness specifically with the DOM. Any hints about how many DOM calls am I making in each of these lines of code? Like, can you take a look and take a guess? So a DOM call means a transition. There's actually 5 because the last one is just a call on that object. So I was making 5 DOM calls, so 5 transitions from JavaScript to DOM and then back. Now instead, what I could have done is like if I'm using those elements again and again, I could have actually cached them and made one call in my perf critical code. That would have saved me a lot of time in terms of and helped me improve the performance of my app a lot. Second, avoid automatic conversions from the DOM. Now in my app, I showed you like a slider, right, wherein I was kind of sending in a board size that I kind of showed it to you. Now, I did not imagine this, but like the type of that value that comes from the DOM is actually a string. And I ended up spending like 25% of the time that was taken up by my initialization function was actually just spent in converting those types from string to integers. So the key thing when you're getting values from the DOM, check for their types. Like if you want to use them as integers, use parseInt and make sure that they're coming back as integers. And the third key thing is like paint as much as your users can see. Like displays have a native frequency, right? Like, so typically our monitor is 60 hertz, so around 60 frames per second. That's what, you know, human eye also kind of tends to do. But in terms of like when we are writing, you know, set interval and set timeout, we end up saying like, okay, let's use a timer value of 0 and let's see, you know, how fast it can go and you know, do the work. That's not the right way you should be doing it. The best way you should be doing is try to use request animation frame, because on any machine it will try to meet the native you know, display frequency that is supported by that machine. So always the best practice. But there are cases wherein, like for down level browsers, etc., you might not be able to use request animation frames. So, you know, in those cases, when if you're using set interval or set timeout, try to kind of put them to a frequency level of, okay, you want 60 frames per second, so let's do these animations at 60 frames per second. Now, with all of these things said, let's go back to the app and see what's happening in the app and how we can go and make it run faster. Now, you know, the first thing in terms of improving the, you know, amount of work that we are doing, I was actually using this, you know, copy benchmark matrix wherein I start from a known shape, etc. And in terms of this code, what you see is like, okay, I have a, you know, huge board, I'm kind of parsing it. And then what happens was like, I'm actually doing a lot of CSS manipulation on my code to actually go and, you know, get the array state back to, you know, where we should start from. So there's also a lot of CSS magic happening at this place where I'm actually, you know, kind of putting my board to the right shape. So now, and when I go to my animation loop, this is actually the animation loop that I was working with. You know, one of the things I noticed was like, yes, even though I was creating this, you know, benchmark, which is good, I have gotten to around 5,500 rotations per second, which is great because that will continue to be the same. But let me just, you know, go and avoid this extra benchmark, and instead, starting from a known point, let me just create a known point randomly and run the game. So with these changes, let's go back and try to see like how does the app perform. Let's go click the benchmark mode. Now what do you see? Like suddenly from less than 60, it has gone way up, right? It's performing a lot more in terms of frames per second and what's happening in the engine. Now one of the other things that happened was, let's go look at this. Now I was actually doing an animation of 0. So save this, go back in my app, hit Control F5, run it in the benchmark mode. And then you'll see that, you know, I'm kind of like, once I've done that trick as well, you know, I'm kind of getting 60 frames per second more or less. Like the key reason it did not improve was like there was also a lot of CSS animations that were happening in my app that I actually had to go and fix to get the, you know, get the performance needed. And this would actually sustain even if like I go improve the matrix size, it'll still kind of be at around 60. So, I mean, in terms of the frames per second, you know, here's the meter. Like, yes, it is kind of like performing well. And like, how many of you think that the transitions that are happening are like fairly smooth? Like, you would love to ship this app with these kind of transitions? Anybody? Okay, one person. Okay. Okay, most of you. Because this kind of brings me to the end of my talk, and just to kind of close on it, you know, the thing that I did when I changed my animation timer and kind of started using the 60 frames per second and request animation frame, you know, one of the things that I noticed was like the overall CPU utilization that the, you know, profiles were showing me actually came down somewhere from around 75% if I was to draw like a straight line to 65%. Now, whenever you think of CPU cycles, think of battery life. Like your app can actually run 10% longer. So CPU cycles are extremely, extremely important. The other thing that happened was like my problem was solved and I was able to get a visual throughput of around 60 frames per second. Now, the key thing why performance really matters and like why this responsiveness matters, why you should save CPU cycles is like one, of course, it is providing a great user experience. The second thing is like by reducing those CPU cycles, you're providing longer battery life, and users love applications that don't consume as much CPU as some of the other bad applications which have similar behaviors. And the third key thing is like in that 10% CPU cycle that you saved, one of the things that you could actually end up doing is you could actually end up doing more work, make your apps more rich. So I could have done like different kind of transitions, one for one player type, the other for other player type. So that's one of the things you could also do. Now, in terms of all the optimizations that I talked about, they're available at this tiny URL. So till now, I was talking about aka.ms/fastjs. Now you can actually go to faster.js. This is not the fastest JS. Like you can go look at the code, you can apply a lot of the other principles and make it go run faster. And like, come see me tomorrow morning at the Visual Studio booth and tell me like if you've been able to make it go super, super fast. I'll love to see it. So just to recap the 5 principles that you should always keep in mind. Principle number 1, stay lean, use less memory. Principle number 2, use fast objects and do fast object property manipulations. Principle number 3, always write fast arithmetic, use fast numbers, make sure you're using integers when possible. Principle number 4, use fast arrays, like make sure you're aware of the implicit allocations there as well, like you're not transitioning anything in the perf critical code. And principle number 5, do less, specifically less cross subsystem work. Like that's really, really expensive in terms of the code. Now, here are some of the other talks that I kind of thought might be useful, like the ones in bold are the talks that are still going to happen. I would definitely recommend that you go to the UI responsiveness tool talk tomorrow morning by Jonathan Carter. That's going to be probably pretty awesome in terms of figuring out the bottleneck of your code and how you could use that new tool that we are shipping. And that brings me to the end of my session. Thanks for attending, and please do submit your feedback. It is, thank you. I think we are definitely out of time, but I'll be hanging out here. If you guys have any questions, I'd love to take them.